Okay guys, as I mentioned in the previous video, we will be doing some more problems on second law of Newton and solving this particular problem now in the elevator. When you are comparing now the real weight versus apparent weight, I will have to introduce a third law of Newton, and so that you have a little better understanding on how the second and the third law I guess can be combined to solve these kind of problems, which for the novice they look a little formidable. Now, what is the problem now? So let me read it and then we'll solve this problem. So this is the following problem, guys. Your mass, let's say, is 92 kilograms, and you're standing on the scale. And again, if my handwriting is not that great, I'm always reading the problem so that you can always pause the video and rewind the video. So your mass is 92 kilograms, and you're standing on the scale in the elevator. Starting from the rest, the elevator accelerates 2.50 meters per second, and then continues at constant speed. What is the scale reading during the elevator's acceleration? Okay, again, if you cannot, guys, read the my handwriting here, I'm trying my best here. Just rewind the video and just copy it as I dictate the problem. Okay, so how do we solve this kind of problem? Well, the first thing we have to realize that if you're just standing, and again, sorry for my drawing, guys, I try to be as simple as possible, draw everything. If you, let's say, standing on the elevator and just standing without any movement, the elevator right now in stationary position, what's going to happen, if I'm going to draw now a free body diagram, there is, of course, you applying the force of, I guess, of gravity is pulling you down, and that is your, there is your weight. F sub g is equal to m times g, and there is also, of course, a force that the scale exerting on you. This is where we're going to mention the third law of Newton, and what it does, it pushes back the scale, F scale, it pushes back, and it pretty much exerting the same force as the gravitational force. Now, according to the third law, Newton's third law, all forces come in pairs, and so let's say F sub A on B will be equal to minus F sub B on A. In other words, let me just make it a little lowercase. In other words, if there is an action, then that means there's going to be always reaction. If you again standing on the floor, you may not know it, but the floor always is also acting on you, because if it doesn't, it will just break and you will just go, I guess, to the ground. Now, so again, this is the free body diagram here, and when the elevator is not moving, you're pretty much standing on the scale, and it gives you the real weight in this condition, guys, in this particular situation. Now, and again, I just mentioned Newton's third law. It's to summarize it, that all forces come in pairs. And again, if I if I'm standing and act on the floor, according to Newton's third law, the floor must act on me also with the same force. Now, what happens if I actually now stand on my, and by the way, this real weight is everywhere pretty much the same as long as you move around the surface of the earth. It's pretty much stays the same. But what happens if you're standing in the elevator on the scale? You're standing on the scale, and then the elevator starting actually moving upwards. It's starting moving upwards. So what happens now to your weight? And to answer this question, first we need to analyze what happens to the velocity. And as you move upwards, remember we already dealt with the vectors before, velocity vectors. Let's say this is v1. Now the greater velocity will be now vector 2, and it will again accelerate with the same constant, let's say, acceleration. But what's going to change here is the velocity. So now, where is the acceleration will go here? Well, remember, guys, when we try to find the delta v, we do the v final always minus v the initial. And then, so what happened? Remember how we add the vectors. So this vector v3 will be now, this will be taken and flipped. Remember, when we add the vectors, we flip the first vector when we try to find v final minus v initial. And so the resultant will be right here, and that resultant will be the wv, and this is v sub 2 now here. Okay, again, if my drawing is not, guys, legible, I am actually explaining everything in terms. So again, just rewind the video and just label it appropriately. Now, so if my delta v is looking upwards, and I'm going to create this coordinate system, which I usually use to figure out my signs. So this is the y-axis, this is the x-axis. So this is a positive direction, this is a negative direction. Okay, so if I'm accelerating upwards, my acceleration is lined up with the delta v, which is upwards, and so my acceleration is positive. Okay, so my acceleration is positive. And remember, the acceleration is directly, guys, related to the force, second law of Newton. We talked about it already. So my force now, additional force now will be F net. Let me try to draw it a little legibly. F net will be also looking upward. So when you accelerate, guys, in the elevator, what's going to happen here, let's say I'm going to draw now the free body diagram. So it's going to be now this force that the scale exerts is going to be higher than the force that related to your weight, which is F sub g, and this one just F scale. Again, so when you were stationary here, these both forces, scale and your weight, real weight, were the same. But once you start accelerating upwards, now you are disturbing, you have no more, an equilibrium anymore. So you're adding a little net force to the force upwards, and so the force of the scale now becomes bigger than it used to be at equilibrium. So now you got a little bigger here, force of the scale. Okay, so what does it mean now? How is it going to help us solve, guys, the problem? All right, so let's go back to the problem and see if we can solve it. Now, using our same approach as we did before for our tug of war problem. Okay, so let me just erase all of this. You guys, captured it. And you can always send me an email if you're not clear about something. All right, so let's take a look now at our accelerating elevator here. So I'm going to put you here as a dot, and then I'm going to put the F sub g in here. And then, of course, we talked about your F scale contains now the F sub net. And so how do you set this problem up and solve it? Well, let me first state what's given here. Given. Well, let me just erase this. I meant to put the columns here. Okay, so let me see what's given here. Now, so we are given a mass of 92 kilograms. Okay, and what else is given? Well, I can see here acceleration here is 2.50 meters per second square. That's also given. And I've been told that it accelerates at this particular acceleration, which is constant here. So I already captured that. And that's pretty much all that I need in here. And so the question is, what is the scale reading during the elevator's acceleration? So what I need to figure it out, guys, now is I need to find out F scale question mark. All right, so how do I do this now? Well, remember guys, from our previous discussion, I can now do the following. Well, how do I find the F subnet? It must be F of the scale plus minus F sub g here. Okay, I'm almost there. So, in other words, I can find out this because I already have mass and acceleration here. It's part of this F subscale. And all I have to do now, this is the unknown, question mark. I know this. This is m times g. And how does it visually look, these vectors? How do we add these vectors up? Well, again, I'm going to draw this vector, F scale. And then I'm going to place now this vector here. It's looking going downwards. So this is F sub g negative. And then my resultant here is nothing as what? F subnet. So this is conceptual here presentation. Oh, I'm representing now this conceptually, and mathematically this is exactly what it means here. Okay, now, so how do I find now F subscale? Using simple algebra here is equal to, I'm going to bring this one over to the other side. That will be F net plus F sub g. Okay, so all I have to do now is I have to just plug everything in, and I will solve for F scale, which will be nothing else as the apparent weight, guys. All right, let's do it. So F scale is equal to, now I'm going to try to, you know what I'm going to do? I'm going to try to now lower it a little down because I may not have space here. So I'm going to put down here F scale is equal to, so F net. So F net will be the mass times the acceleration plus Fg, which is, we know Fg is nothing else, guys, as your mass times the g, which is acceleration due to gravity. So let me plug everything in right now. So the mass is, well, I can actually rearrange it in the following way and just take m out, a plus g. Again, this is simple algebra. I just factor out my m and just start plugging things in. 92 kilogram times acceleration that gave it to me, 2.50 meter per second square, and it's in parentheses, plus 9.80 meter per second square. And again, if you can't see, cannot make out these numbers, just rewind the recording and just listen to my explanation. All right, so what do we got here now? What's the answer? Well, I'm going to use my calculator. Let me just get my calculator. It's stuck a little here. Okay, and again, always do mathematical operation first in the parentheses. So I got 2.5 plus 9.8, and again, remember when we add, we always have to round it off to the, we're using the precision rule. So in this case, we're going to round it off to the 100th place. So my answer here is 12.30, in the parentheses here, 12.30 meter per second square. So I got 4 significant figures. The reason I did not add zeros in here, because it's just, it will give me still the same answer. The calculator does not know the significant figures. Okay, and the next step, so I got 4 significant figures here from this calculation, times 92 kilograms, which is now 2 significant figures. So this is the f of the scale I got. Okay, so let me just put it down here. Let me just make sure that I use the right number of significant figures. Okay, that will be, let me just write the whole thing, 11316. And again, we have kilograms times meter times second square. This is nothing else, it's just units of Newton. Okay, and so my last thing will be significant figures. I only have 2, so there will be 1.1, 10 to the 1, 2, 3, move 3 times the decimal. So I'm going to put power of 3, and that will be Newton. And that's how you solve the problem with real versus apparent weight. When the elevator is moving up, you just set up the problem, use a combination of the second and third law of Newton, and we're going to do some more problems.